So I had an interesting weekend, of course, grading the exams. I'll just start with, it was interesting. On the good side, there were, by the way, there are limited things I can talk about here because there's still some students who haven't taken these. So I'm going to be careful about what I can say. There was at least one person who got a perfect score. There were a number of scores in the 90s and the 80s, which is good. After that, things kind of went south. Had me scratching my head for a long time. I took an extraordinary step of going back and kind of mining for partial credit where I probably shouldn't have. But as it is, I would say a third of the class is just great, just fine. Another third is kind of, well, could go either way. If you have a score in the mid-70s, that's like a C grade, but you know, if you kept that through the class, that would be fine. And about a third of the class is deeply in arrears at this point. You know, every person is different. Every exam is different. Some of the basics that we went over just weren't there. And as I said, I was scratching my head a lot, and I realized I had been negligent in a certain area. I hadn't really kept on top of the homework. But this morning, well, last night, I kind of pulled out a spreadsheet with homework, and I noticed it's very sparse. There's not a complete correlation, but there's some students who did very poorly, turned in almost no homework, which is, you know, in my head, it's not a surprise, but it makes me think that I've been delinquent in expressing the need here. I mean, it's like I was giving a class in bicycle road racing. And I said, here's the theory, and go out and practice. And instead of going out every day and riding around the track, somebody just showed up for the midterm and didn't do very well. So I'm not short of giving a little lecture here. I know it's been a really hard semester for a lot of people. Things are very different this year. With COVID and absentees, and some people just suffered. You know, there's usually a few random difficulties people have. But I guess what I'm trying to get out is that I know this class is important to a lot of people, not so much that you have to be skilled in calculus when it's over, but it's a hurdle, whatever major you do have. So I'm trying to think of the right approach. I mean, I've been very flexible. I thought being flexible with the homework was a good thing because I know there's a lot of stumbling blocks showing up for people. But if you if you haven't gotten the message, right, that you need to do the homework, you need to practice this, you can't just come in and listen to the lecture. Well, some of you can, but those who can, I'm not speaking to you, right? There's a few people in here who it wouldn't matter. But for a good portion of the class, doing the homework, if you have difficulty, working with students, coming to the math department sessions, coming to my office hours, it's really important because you're going to, at this point, some of you, if you kept going the way you're going, there's no way you're going to pass the class this semester. And I'm not here, I'm not trying to shame anybody. I understand it's been a difficult time, but there are certain things you have to pick up on quickly when you come to college. You have to defer a lot of what might be more enjoyable things to do with your time. Hanging out with friends, listening to music, whatever it is you like. It's fine when you get everything else done, but for this class, you can expect that you're going to need to spend quite a few hours each week if you're going to learn the subject and get through this. For some of you, it's more important than others. I mean, if you're in a science or you're a math major, obviously you're not going to get by with passing the class and kind of putting it behind you, but in any event, you have to get over this hurdle. Now I'm here, I'm going to try and help every single one of you. I don't think anybody is a lost cause at this point. The only thing that would make that happen is if you decide, well, I'm not going to do anymore. I'm just going to do what I've been doing and see if it works. And I have no control over that. But one of the problems you deal with right now is that what we've done so far, I'll just say, learning how to find a derivative of a function. That's the basis for what's going to go on in this class. If you haven't gotten that down really well at this point, you need to remediate that. Now, having said all that, I know some here haven't taken the exam yet and will, and I don't want to frighten you. Hopefully you're ready. I can't really return the exams until Thursday after class, and I would recommend any of you who thinks they need a running start from where we are, come by after class on Thursday. I can hand back your exam once I get the other students started. I will stay as late as I need to talk to people about the exam, go over problems, but it's up, again, I know I'm not speaking to everyone here. There's a number of students who did just fine. You probably know who you are. If you're not sure, I put the grades up on Canvas. And I'm open to feedback. If someone wants to tell me I'm doing something the wrong way, or maybe I should be tougher in some area or easier in some other area, that's fine. But the basic bottom line is you have to be able to do these problems. You have to understand the material well enough. I don't want to say any more about what's on the exam, because there's still people who need to take it. If there are any questions or anything anybody wants to say, either you can say here or you can come visit me in the office and fine. And you know, if you've been doing the work and you've been hanging in there and you've been doing okay, hats off to you. I don't want to, this isn't like supposed to be some kind of shaming anyway. Keep doing that, and I'm sure you'll get through this, and you know, you'll do okay. But that hasn't been what's going on. You must know that, and I'm just telling you in advance, it's not going to work. So, all right. You had a problem you wanted me to go over?
Yes.
Would you put it up on the board, because I don't have a book with me. Just let me know if you can what page it's on, and so everybody can see where it comes in. If you don't know, just write the problem on. I'll bet somebody in the audience will figure it out.
I know what problem number is, though.
That's
That's all I know.
Oh, linear approximation. Okay, good. All right, so obviously there's no limit to the value of reviewing stuff. So our linear approximation formula goes something like this. That is to say, we have some function. We know the value at a point on the function, and we know the derivative, which is the tangent at that point. If we want to, this is my x, and if we want to know a point that's pretty close, h, I can use a linear approximation. Imagine the function is a straight line at that point. And so this formula will apply as an approximation. So the question is, what does this problem want us to do here? In a sense, it's a bad problem because you could do all sorts of things. You could treat this as cosine of 28.5 plus 0.5. But that really wouldn't, you know, imagine you're on a desert island without a calculator. You just, you know, it's not going to help much. So clearly what they really want you to do is they want you to express it this way as cosine of 30 degrees, an angle that we know the value of, well, are plus minus 1 degree. So what does our formula tell us? It tells us this is the cosine of 30 degrees plus minus 1 times the derivative. Well, now we have a little problem here, a difficulty, which is we don't know what we could figure out using the chain rule, but using cosine, trying to find the derivative of cosine in degrees is not the same as finding it in radians. So we have a choice. We can either try and figure out what that is, or we could switch the problem to radians. I think that's probably the smarter idea, because in the end we'll end up with something easier to deal with. So, all right, let's 30 degrees in terms of radians.
Pi over 6. Pi over 6.
Pi over 6. But we're also going to have to deal with 1 degree in terms of radians. So I'm kind of lightheaded today for reasons you might imagine. So I'm going to have to think about the conversion factor. So 1 degree times pi over 180 degrees, right? Which is pi over 180. All right, so really what I have here is cosine of pi over 6 minus pi over 180. So that's going to be equal to the cosine of pi over 6. Might as well just put a minus here right now. All right, so now I have my h, I know, is pi over 180. And now I have to find the derivative of cosine of x, which at this point, hopefully you know, is minus the sine of x. Again, in radians. So we have another minus sign here. Just going to make these plus the sine of 30 degrees. All right, so that's the hard part. We know, well, pi over 6. So now all we have to do is dig up our trigonometry. All right. So pi over 6 is a 30-degree angle. You should recognize this as a 30, 60, 90. This is 1, this is a half, this is square root of 3 over 2. So this is the sine is a half, and the cosine is square root of 3 over 2. So that tells us this is square root of 3 over 2 plus pi over 180 times a half. And it does seem kind of silly, doesn't it? And I can just figure it out directly, but let's see what we end up with. Square root of 3 divided by 2 plus, I guess this is going to be pi over 180. Let's see if that, well, this is 0.8835. And if I were to switch over to degree mode and ask what the cosine of 29 degrees is. Huh, that's it. I feel like I must have done something wrong. That's not a very good approximation, is it? All right, so I probably made a mistake here somewhere. Let's see. 1 degree is definitely pi over 180. Oh, wait a minute. Did I do that right? No, I didn't. I left out the half. Let's try that again. Square root of 3 over 2 plus pi divided by 180. Oh, I did it again. I don't know why I can't. Square root of 3. My fingers want to do one thing and I want to do another. Divided by 360. You know, we all have bad days, don't we? Plus pi divided by 360. So here I get 0.8747875. It's, you know, so that's the linear approximation. You know, of course, use a calculator and you can get, the right answer, and you can see how close we are. So you might ask, what's the point of this? Well, the point is, we're trying to learn a technique which will have use in other circumstances where we don't have this, we don't know the function that well, but maybe we can find the derivative and we can do an approximation. So this is just kind of a little baby problem to see that you know the technique. Nicole? Sorry.
I got pretty close, but I couldn't figure out what to do with the negative 1% because we had only done, up to this point, we had only done linear approximations with numbers that we could take away from, like.
In other words, here I'm making h a negative number.
Yeah.
It works, well, again, we can go h on either side, right? So this is kind of a negative h that we're subtracting. Yeah. All right, was there any other homework anybody had a question about before we move on? All right. I was planning on the video to just start now, but seeing as how a few people came in late, you might want to hear what I had to say. I will put that on the beginning of the video. I guess it might help people who aren't able to attend today too. Something else I wanted to say before I got started, but I don't remember what it was. So there you go. Now this is like my darker side, but it's not really me. It's Christine in the math office wanted me to remind people that in about a month, sometime in early April, there's the last day you can drop the class or withdraw. I hope nobody feels they need to do that, but I would understand if they did. It's best to do that if you get to that point and you feel you're not gonna complete the class. It'd probably be better to stop at that point and try again rather than get a failing grade. But I don't know. It just depends on details I don't really know about. Okay. The main topic of today is maximums and minimums. And I'm going to start looking at function, well-known function x squared. It's a parabola, kind of looks like this. And I want you to think about the derivative on this side of the parabola. The tangents have a positive slope. And on this side of the parabola, they have a negative slope. And as we move down towards 0, well, they both start to flatten out. And it might be reasonable to think that the point where we hit the bottom is exactly the point where the tangent is horizontal, or that is to say the derivative is equal to 0. That would be the case. That tells me for a smooth, a continuous function like this, a differentiable function, that if I can find out where the derivative is 0, I can find a place where the tangent is horizontal, and in the case of this parabola, it's a minimum. Now, let's just do a simple example. So, if I wanted to find, the minimum of this function, this is also a parabola, I would find the derivative is negative 2x, and I set that equal to 0, and sure enough, at 0, x equals 0, the derivative is 0. But the function at 0 is going to be 3. All right, well, at this point, we have to take a look at what this looks like. This 3 minus x squared is going to look like this. This is 3. But this clearly is not a minimum, it's a maximum. So this feature of the derivative being 0 doesn't tell you whether it's a minimum or a maximum, necessarily. It tells you it could be a minimum or a maximum. All right, so I want to take a look at a somewhat complicated function, just to give you some idea of what could be going on here. So just imagine this is a nice polynomial function. Could happen. And we look at this function and we think about, well, where is the derivative 0? So really we have something here, something here, something here, here, here. Well, this function goes off to negative infinity and positive infinity. So none of these represent what we would call the absolute maximum or absolute minimum, right? So instead, what we're learning is that where the derivative is 0, we have a local maximum or a local minimum. And just knowing that the derivative is 0 doesn't tell us which of these it is. That's something we'll look at in a few minutes. I guess we want to have a little better definition of what a local maximum and minimum is. So if we have an interval, so I want to say we have some number c is on this, some interval, some finite interval, a closed interval, and f of c is greater than or equal to f of x for all x on that interval, and c is a local maximum. And of course, f of c is less than or equal to f of x for all x on that interval. C is a local minimum. So those are just the mathematical definitions we give these. So in order for these things to be local maximum or minimum, there has to be some interval A, B, for which this is the case. Clearly you have to choose that interval properly. Choose an interval from here to here. Which of these is the maximum? That's not the issue. Because they're within their own boundaries. They're locally maximum or locally minimum. All right. There's a few little nits you have to go over with respect to this. Let's consider a function that looks like this. Get this right. A here, B, C, and D. So these are endpoints to the function. It's only defined, its domain is limited. Well, again, we see that we have a local minimum at B and a local maximum at C, but in fact, the function is greater at A. That's its absolute maximum. And similarly at D, we have a lower value than anywhere else on the function. So this is an absolute maximum. This is a local maximum, local min, and the absolute minimum. So we, again, like mathematical definition for this absolute maximum and minimum, and it's very similar to the definition of the local. If C is the member of the domain of F, and F of C is greater than or equal to F of X for all X, member of the domain, and C is, well, F of C is an absolute maximum. And similarly, F of C is less than or equal to F of X for all X member of the domain of F. F of C is the absolute minimum. Okay, so well, there's one more nit I want to look at. We have a function, f of x is the absolute value of x. It looks like this. Well, look at the graph, you can clearly see that f of 0 equals 0 is the minimum. If we look at the derivative, right? The derivative of x for x less than 0 is just minus 1. And the derivative for x greater than 0 is 1. but it's not differentiable at that point. It's kind of a spike here. Well, we have a name for this kind of point. This is called a critical point. It's a point where the function is not differentiable. And so when we're seeking out maximum, minimum, either absolute or local, we need to look at all critical points and check them. So, I'm going to do some examples in a minute where we look at a function and we ask the question, what are the local maximums, or the absolute maximums and minimums? There's a few important basic ideas, some in the form of theorems that apply. So let's take a look at those. You don't have to know these by name, but you should understand the idea. The first is called the extreme value theorem. And it says that if you have a function, f of x, which is continuous, on a closed interval, I'm going to come back to the fact that this is a closed interval. That's actually quite important, as opposed to an open interval. Then there exist values C and D on that interval, where f of C is an absolute maximum, and f of D is an absolute minimum. So let's think about what that means. You have some function, any function, it's defined between A and B. And it can do anything, you know, it can be very crazy. But it will have an absolute maximum and it will have an absolute minimum. Sounded local. Okay. Now you might say, well, why does it have to be closed interval? Well, consider the function f of x equals 1 over x, and consider it on the open interval 0 to 1. Well, it does have a minimum. At 1 it's 1, so that's the minimum. But it has no maximum. So that's the reason closed interval is important. Okay, that's the extreme value theorem. basically tells us there will be a maximum and a minimum under those circumstances. I guess, you know, why does it have to be continuous? Well, it's kind of the same issue. You could have a function that looks like this, or go down, and on this closed interval, there's no maximum, but then again, it's not continuous at this point. So, all right, the second item is called Fermat's theorem. Anyone here heard of Fermat before? Okay, well, Fermat's a famous mathematician. He has his name on a number of theorems. The most famous is called Fermat's last theorem, something he didn't prove. It's only a big puzzle in mathematics for centuries. And only in, it was in the 90s, was finally, the proof was completed. It's a cute little theorem. So think of the Pythagorean theorem for a second. This is not really a part of our curriculum, but I think well-educated students should know this. And you know that there are certain numbers, certain integers you can plug in here, like 3 squared plus 4 squared equals 5 squared. 4, 5. It's known as a Pythagorean triple. There are many, an infinite number. As soon as you find one, you can always, you know, multiply each of these by some square, and you get another one. But there's even an infinite number in, you know, lowest terms like this. Fermat's last theorem says if you look at this equation, where n is some number greater than 2, it says there are no integer solutions to this. There's no triples. And it took a great amount of effort to solve this. That's an interesting topic on Google. Fermat's last theorem. But what's the Fermat theorem that we're interested in? Fermat's theorem says if a function f of x has a local max or min at c, some c, and if f of x is differentiable at c, and the derivative at c is 0. So what are we saying here? You have a function, it's got to be continuous to be differentiable. It's differentiable, it's kind of smooth at that point, and it's a maximum or minimum. Then the tangent has to have slope 0 at that point. If you kind of play devil's advocate here, let's say I had some function and I say this is the maximum here, but it's got, you know, the derivative is positive. Well, means the slope is kind of moving up at that point. There has to be some point close that's going to be higher. So that's not a proof or demonstration. It's just a way to think about it. The derivative has to be 0. Now, again, it has to be differentiable. So, you know, if you have some function that just happens to have a spike at this point, well, even then, oh, I know what we're looking at. No, actually, I don't. I'm trying to think of, is there a function which isn't differentiable and it has a local min, but it's not, but the derivative is, well, the derivative, it's not differentiable, you can't ask what the derivative is, so that doesn't really matter. All right, so that's second item that's useful to keep in mind. Third item the book specifies is kind of it's an algorithm, it's a method for finding absolute maximums and minimums. If you have a closed interval. So we'll find the maximum and the absolute maximum. On a closed, continuous interval first step is find the value of f of x at all critical points. Well, you define a critical point as a point where a function isn't differentiable. Since it's a closed interval, there'll be endpoints where it's not differentiable. So the endpoints are 2 points you need to check. And if you have any spikes in this, you know, there's like an absolute value. If those spiking points, you have to also check. Oh, well, okay. The book defines things a little different. To me, they say also check the endpoints. Guess they're defining, guess they're also defining points where f of x, f prime of x equals 0 is critical. I guess that's it. And part C is find the largest value of the above. And the largest and smallest. So, you know, looking at a diagram like this, you look at the endpoints, look at any critical points. I guess they're calling places where the derivative is 0 critical points. You find the value at all these points, and you go through them and find where the value is the least and where it's the greatest. And that tells you the absolute maximum. All right, I'm going to stop here for a few minutes, take a break, and we'll come back and do some examples.
As long as I can bring up like C2 values, and so on and stuff like that. No, it's like those it's like the polar kind of like math nerdy like scene guy. I just have to start going like I need to like work through problems that like somebody there would be like this.
We're going to get started in a minute. I just want to say I really like to lead all this on the blackboard, but I can't. So hope either you jotted it down or it's in your head, or when I bring it up, we'll make reference to it. Oh, good. He's back. So we have, what do we have? We have derivatives at 0. We have local maximum and minimum. We have absolute maximum and minimum. We have critical points. You know, before I get on with this subject, there's some more. You know, some people came in late, and I recommend they take a look at the beginning of the video. It's not math, but it's important. I also, I'm gonna be in my office hours after class. If anybody who's concerned about things, come talk to me. I think I have some people taking the exam today. I'll have to get them started. And we can look at your exam if you want. I have it. I just can't hand it back until Thursday. All right. So let's look at an example here. Say we have the function f of x equals absolute value of x plus 1 plus 2. And we want to know about any local maximums and minimums. Derivative of this function is 1 for x greater than minus 1, and no, my hand is not writing what I'm saying. 1 for x greater than minus 1, and minus 1 for less than minus 1. And it's the function is not differentiable at minus 1. So that's a critical point. Just as a shortcut, when you see an absolute value where it becomes 0, that's where it's going to switch. If it was positive, it's positive, but if it was negative, it becomes positive. That's typically a critical point. So we want to see if minus 1 is a local maximum or minimum. Minus 1 f of x is 2. And Okay, so that's, you know, that's our possible critical point. That's our, you know, potential minimum or maximum. And I think you can see pretty clearly it's going to be a minimum. Because for any value other than -1, you're going to have a value greater than 2. All right. Next example of x is going to be a polynomial. But we're only interested in the interval -1, 4. So we're defining this function with this domain, and we want to find the local maximums, local minimums, absolute maximums and minimums. So the first thing to do is to find out where the derivative is 0. So we have 12x cubed minus 48x squared plus 36x. We're going to set that equal to 0. Looks like we can factor out a 12x and we get x squared minus 3x plus 3. Is that right? No. 4x plus 3 or 12x. X minus 3, x minus 1. All right. So this is equal to 0 at x equal to 0, 3, and 1. So those are the possible local maximums and minimums. But we also have the endpoints. So that's -1 and 4. So let's figure this out. At -1, we have 3 plus 16 plus 18. Is that right? 37. At 0, we have 0. That was easy. At 1, we have 3 minus 16 plus 18. 1? No. 2 is 5. And at 3, I'm not going to figure this out. I'm just going to cheat. And also at 4, it's 32. All right, so these are our values. So our absolute minimum comes at F3. And our absolute maximum comes at the endpoint, -1. So that's just, you know, how you go about figuring these things out. Let's take a look at a different kind of problem. Any questions about what I just did? There's some work here, right? You have to plug in these not so nice values into polynomial. Okay, so f of x is equal to 1 over x minus 1. So the derivative is what? use either the quotient rule or the reciprocal rule. For instance, this was a topic of, this was a problem on the exam. I'll go ahead and write it all out in terms of the quotient rule. So derivative of 1 is 0, so this goes away. Wait, derivative of this is minus 1 over x minus 1 squared. Okay, so we want to set that equal to 0. Well, it's not 0 anywhere, is it? So there's no critical points here. Its derivative is, you know, it has a derivative on its domain, which is everywhere but 1. And so there are no extreme values. There is no absolute maximum and minimum. And if we were to graph this function, you would see, of course, that it has an asymptote at 1. But of course, you know, as you get close to 1 on either side, it will get as large or as small as you wish. So there is no absolute maximum and minimum. All right. Now, this is like the problem that, you know, the exception that proves the rule. That doesn't make any sense, does it? It's an exception. The rule isn't always right. So let's say we have some function. It's equal to 2x for x less than 1. And it's equal to half of x plus 3/2 for x greater than or equal to 1. So it's differentiable everywhere but 1. So the only critical point is 1. And what is it at 1? It's 2. So the question is that an extreme point? Is that an absolute or even a local max or minimum? Well, let's graph this and see what's wrong. So 1/2 x plus 3/2. So it goes through y-axis at 3/2 and has a slope of 1/2. Trying to draw this. But at 2, its value again is, isn't that right? At 1, I guess its value is 2. And get the slope right here. So we have a critical point, but it just doesn't happen to be a max or a min, right? This function, just like this function, has no absolute, no extreme values. So this is just something, you know, to be aware of. Obviously, the derivatives where it is defined can't be 0 either. It's always a positive value. So those are some examples on trying to find maximum and minimum values. Oh, there's one more of these kind of exception that proves the rule things. It's a little different. Take the function f of x equals x cubed. Defined on all real numbers. Well, derivative is pretty straightforward. That's 2x squared. And if we set that equal to 0, we find out that...
Three x squared.
Thank you. Now, here's a question. Did I say 3 or did I say 2?
You said 2.
Oh, okay. So I was completely wrong. Can't blame my hand. Thank you. So at x equals 0, we have the derivative of x equals 0. Wait a minute here. What does this function look like? You know that x cubed kind of looks like this. What is this telling us? Well, at 0, the tangent is horizontal, but yet there is no max or min, no local max or min here, certainly no absolute. This kind of point here has a name we're going to look at a little bit later, called a point of inflection. And I might as well start trying to get you to see what this thing is really about. You'll notice here the function is curved, kind of curved down. Here it's curved up. So the point of inflection is exactly the place where this switches. It doesn't have to have a derivative of 0. It could look something like this. Right? Well, there's no, the tangent is certainly not horizontal here. But here we have a function that sometimes we'll say it holds water, and over here it kind of loses water, water falls out. Think of inflection. Okay. It's too late to start the discussion here with this, but finding maximums and minimums is one of the most common things we use calculus for, differential calculus. It's a really powerful way. We have a function described analytically, and we can find its derivative and see where it's zero. We can find, a local maximum or a local minimum. So this is a really important subject. We'll come back to it quite a bit, but this is the basics we're doing today. The next question that comes up is we have some function, and we know that at some value c, the derivative is 0. So we know at that point the slope of the tangent is 0. It's a horizontal tangent. But the question is, which is it? Is it a max or a min. It's not always obvious just from looking at the function. So let's go back to this where we started. We have a function of x equals x squared. And we know that, you can see it's a minimum, but let's look at this a little bit. To the left, we have a derivative that's negative, becomes 0 and becomes positive. What's happening along the way? The derivative is decreasing, becomes 0, and then, it's negatively decreasing. It's actually increasing, right? Here it might be, say, -2, and here it might be -1. So it's increasing. Here it's 0. Here it's 1. Here it's 2. So that's the derivative, right? Well, what do we know about the change in the derivative function? The derivative is the change, in the slope of the function, but what's the change in the derivative? That's the second derivative. So we would expect the second derivative to be positive. If we have a minimum. Similarly, if we had a local maximum, what would happen? The derivative would start out, positive, decrease, and then become negative. So if the second derivative is less than 0, we have a maximum. So this is called the second derivative test. Of course, there's one more possibility here, isn't there? It could be equal to 0. Well, that's actually what we have over here, the point of inflection. Second derivative of x is 6x, and at 0, it's 0. So we can't really tell here that this is a maximum or a minimum using the second derivative test, but we find it's a point of inflection. All right, let's have you try a couple of these, see what we can find. Let's start with f of x equals x cubed plus 3x plus 2. I'd like you to find any critical points, any local extreme values. local max and min, or absolute max and min, if there are any. Is that try? Nobody, this is no one's, is it? It's here, someone left it. All right, someone want to tell me what the derivative is of this function? George? 2x squared plus 3. Okay. I set that as... Keep doing that, don't I? Thank you. Appreciate that. Okay, when I go to solve that, what do I get?
Using that too?
Oh, wait. I'm sorry. Oh, that's the problem. Oh. All right, so where is this 0? Where if I solve this equation, what do I find? Nobody? Yeah.
Would you get 1i if you solve it? You end up moving 3 over, becomes negative, divide by 3 becomes -1, and then the square root of -1 is I.
It's actually, could be plus or minus, but it's not a real number, so it doesn't have a local maximum in. I have a suspicion, I might have, when I wrote this down, I might have really wanted this. Okay. It's changed. I know I'm changing the problem line. Okay. So if that were the problem, what would x be?
1 and -1.
1 and -1. All right. And let's try the second derivative test. Second derivative would be what?
6x.
6x. Okay, so at 1, this is equal to 6. And at -1, it's -6. So what does that tell you about the function at 1 and -1? At 1, positive, the slope is increasing, so it's a minimum. Well, what is it at 1? It's 1 minus 3 plus 2 is 0. And what is it at -1? Well, it's -6, so it's a maximum. -1 plus 3 plus 2 plus 2 is 4. 1, 2, 3, 4. And you can kind of fill in the rest. So there's our function, but poorly drawn. When you're doing homework on this, you're either Desmos or your calculator or your friend, because you can just plug in the equation and see if you got it right.
Would you call that the absolute?
There is no absolute.
So there's no absolute like for like sine waves and stuff either? Would that always be like a loop? Like where it keeps like repeating over like along with the x?
Excellent question. I think we'll end with that. So f of x equals sine of x. The derivative is the cosine of x. And where's the cosine 0? Well, many places, right? It's a periodic function. So at pi over 2 and 3 pi over 2, right? Draw a circle.
3 pi over 4?
Pi over 2, this is where the cosine is 0, and down here, 3 pi over 2. Each of these plus 2 pi n, which, okay, let's look at the sine. So here's pi over 2, it's a maximum. Here's 3 pi over 2, it's a minimum. I mean, there's an infinite number of local max and min. But the absolute, of course, I mean, you can say the absolute maximum, of course, is 1, and the absolute minimum is -1.
Even if it does go on forever?
Sure. It's never going to get above 1. Remember the definition.
Because I thought it was only like on a closed interval. I know it was easy to call it.
I'm sorry?
Like I know that we showed that the closed interval was easy to call it like the max or like the.
Well, with a closed interval, you have to check the endpoints. If we use the closed interval here, unless we close off one of these, it's still going to be 1 and -1. But the definition of the absolute max is there's a value c in the domain such that f of c is greater than or equal to f of x for all x in the domain, right? So pi over 2, the value is 1. 1 isn't c, right? C doesn't have to be unique, right? But the maximum 1, there's no other c, there's no other x where the sign is greater. So it's an absolute max. Does that help? Yeah, okay. I think that's enough for today. I'll get downstairs in a few minutes. Anybody think